All right, kia ora, everyone. Welcome to today's webinar. I'm Jeremy Wong. I'm the MC for today's webinar, and I'm also the security assistant from the special interest group of immigrant engineer, which is Caitlin just introduced. So the SIGI is one of the tech groups from Engineer New Zealand, and the initiative was to provide training courses and tech webinars such as thing like today's webinar for all engineers in New Zealand. So we also assist an immigrant engineer in their search of professional employment in New Zealand, as well as we also offering regular events to help you to connect with the like-minded engineer who are just new or just arrived in New Zealand as well, and much more. So this year, our committee have 12 engineers from all stages in their career, and they are all volunteered for their time to support and deliver a good resource for our SIGI members. And if you would like to know more about us, please feel free to come to our website and get to know our upcoming events and our community members. Without further ado, I'm gonna passing on the to our speaker and to introduce of themselves. Thank you.
Yep. Good afternoon, everyone. My name is Vincent Selvakumar, and I'm a passive fire engineer with Origin Fire Consultants, and we are based in Auckland. And here with me today, I have Stephen and Vinny from our team. So what do? We're a specialist fire engineering consultancy based in Auckland, and we have expertise in fire safety engineering, passive fire engineering, and fire protection engineering. We were formed in 1997 as Pacific Consultants. Michael James, who's the principal fire engineer, rebranded the fire engineering team as Origin Fire in 2015. We are based in Auckland, but we do a lot of jobs around New Zealand, Queenstown, Tauranga, Wellington, and Christchurch. Some of our prominent projects are the Auckland Zoo, underwater restaurant in Fiji, pop-up globe theater, a lot of prominent apartments, Fort Highbrook and Oceanside. A bit about myself. I've been working with Origin for about 4 years now. I have a building services background and a bachelor's in mechanical engineering. I have a total of about 10 years of overall construction experience. That's about me. I'll let Stephen introduce himself.
Hi, I'm Stephen. I've been at Origin Fire as a fire engineer for about a year now. A total of about 5 years of fire engineering experience. And prior to that, I was a mechanical engineer. Did my undergrad at the University of Auckland.
Hi, my name is Vinny. I'm the manager for fire protection engineering and senior fire protection engineer at Origin. I've been with Origin for just over a year and in the industry in general for over 10 years. So I guess a bit about my background. I've within the fire industry, I've sort of been in installations and contracts roles, and also worked as an inspector, and I've come back to consulting. Yeah, thank you.
Okay, so with fire engineering, it is actually a bit of a broad field. There's 3 main branches. You get different names for them, but generally you'll find it's fire safety, fire protection, and passive fire. These might be known differently overseas. I know in the United States, fire protection includes fire safety. So just a bit about everything. I'll be covering fire safety. So this is the big picture. It's the fire safety strategy of how the building's designed to meet the building code requirements. We don't specify particular products. We give performance requirements that at different aspects of the building will cover, so need to achieve. Vinny will be talking about fire protection. So this is fire alarms, sprinkler systems, and how they interface with the other building services. Then passive fire, which Vincent will cover, this is about fire separations, how you fire stop services and fire stop and construction joints. So to understand fire safety, the first thing we've got to go to is the Building Act. So the Building Act 2004 has quite a few different sections in it covering various aspects of building. But there's 3 of them that we mainly use in fire safety. There are others that we sometimes use, but these three will cover the main ones. Section 17, which any new work needs to fully comply with the building code. Section 112 and Section 115 refer to when you have an existing building and you're doing alterations to it. The difference between them is Section 115 considers a change of use. So this is where the use of the building, which is defined under the Building Use and Regulations 2005, if that changes, you're introducing different risks and hazards. So we'll need to reassess for that. The difference, what that makes for us is what we need to assess. Under Section 112, anything that's to do with the means of escape from fire, we need to upgrade to comply as near as reasonably practicably, or ANUP. Whereas with Section 115, we actually have more things that we need to upgrade, including fire rating performance. ANUP is a word that you'll hear quite a bit if you deal with fire engineers. So as I said, as near as reasonably practicable. If it's an easy fix, you're going to do it. If it's not easy, it comes down to the life safety benefit in comparison with the cost in relation to the project. So if you have a small fit out, a big upgrade is not reasonable, but if you're gutting the building back to the superstructure, a big upgrade is expected. Below the Building Act, we have the Building Code. This is actually part of the Building Act as Schedule 1. So the New Zealand Building Act doesn't tell you how to build your building. It gives you objectives that you need to meet. So it is open-ended. Oh, sorry, there's three levels. There's the objectives, functional requirements, and then performance requirements. The objectives are quite open-ended. They give you high-level goals, or the spirit of the law, so to speak. An example would be clause C1A, which says that buildings must be designed and constructed to safeguard people from unacceptable risk of injury or illness by fire. Now that is vague, but it covers quite a bit. And below that, you get functional requirements. Again, these are defined goals, but they're open in solution. Example C 4.1a, where it says buildings must be provided with efficient means of giving warning from fire. Again, we're not telling you how to build your building, but the code is saying that you need to provide some means of alerting people. And then past that, you get the performance requirements, which is, these are very testable and quantifiable, and they're specific benchmark. Examples, I'm not going to read it out to you. Clause C 4.3 is quite a long one, but it tells you that occupants must be able to evacuate safely without being exposed to untenable conditions, such as toxic gases, loss of visibility, or excessive heat. There are benchmarks, but your fire engineer will tell you when you do your project. So when we get into the fire safety design, so this might be, it's covered in your fire report. So the fire safety design determines the fire safety strategy. So we'll specify things like your fire safety systems that you need in the building, egress requirements, what kind of fire separations you need, whether it's to protect life safety, to protect property, and we'll give you a rating that you need to achieve. I'll talk more about that later. I'll talk about surface finishes, which is about how flammable your wall, floor, and ceiling linings are. Too flammable, obviously, they're going to catch fire very quickly, and you can have quite a risk to occupants. We also have some interaction with the other designers. As the fire safety engineer, we'll give a requirement. We won't go too much into detail. And we'll say things like, you might require the ventilation system to shut down on the fire alarm, stop smoke spread throughout the building. You might actually use the ventilation system to control spread of smoke, in which case you might say, pressurize this zone, extract from that zone. You'd also have things like your door release, where you say on fire alarm, open these doors so that people can get out safely. And then the good fun one of fire and smoke curtains, which obviously you'll talk to your architect about. So with designing, we've got two main ways to go about it: prescriptive design and performance-based. With prescriptive design, this is the acceptable solutions. These are deemed to comply with the building code. They do have a somewhat limited scope, but they are fairly easy to use. You don't actually need to be an engineer to use them. Anyone can actually write a fire report using acceptable solutions and submit it for consent. You do get a restriction on your design, some things that you can't do with the acceptable solutions that you can do with performance-based design. So when you get to performance-based design, we've got two ways of going about it: the verification method or alternative solutions. The verification method is similar to the acceptable solutions in that it's made by Ministry of Buildings. It's a tool set to verify that your design complies with the building code. There are still some restrictions on scope, but it's generally a lot freer. There's a lot more that you can do. Alternative solutions, you're going away from the verification method. You have no restrictions whatsoever, but it's a lot more, what's the word I'm looking for?
Complicated? Complex?
Yeah, and also there's more regulatory review that you need to do as part of it. With performance-based design, you've got to demonstrate that it works. So you'll do modeling, you'll do calculations. In order to do this, so you don't need to be a chartered engineer to do it, but you need a chartered engineer to carry out, to supervise it and sign it off. So I'm not chartered, but I can't sign off the design. They'll have to go to my boss, Michael. He is chartered. He'll review it, and if it's good, he'll sign that off. Benefits of performance-based design is you get a lot more design flexibility. I've had projects where we had an atrium that they wanted. It would have been full height glass, it would have been hundreds of thousands of dollars to fire rate. We did a CVN2 design, got rid of the glass completely, saved them a lot of money. They were really happy with us. And the last thing I want to talk about is fire resistance ratings, because it is something that's worth understanding. So with fire resistance ratings, there's three components, as you can see, given by X, Y, and Z. So these are about the ability to maintain load-bearing capability, stop the passage of fire, and then also stop the passage of heat. These apply to different components within the fire separations. And your fire engineer will tell you more about it for your project. One thing to note, those numbers aren't based off a real fire, because every fire is different. So we use time equivalence formulas to equate it to the ISO standard fire. That one's a benchmark. It gives you something to compare against. And so when you have fire rated structure and it's tested, they're tested against the standard fire. And so you know, is this good enough for this project? Yes or no. I'll pass it on to Vinny, who will talk about fire protection.
Thank you, Stephen. Just scrolling.
Yep.
I will be briefly covering what fire protection engineering involves in New Zealand, what a role of a fire protection engineering consultant involves, and what does it really mean, and how can we excel in being a consultant. What is a consultant? A consultant is a person who provides expert advice professionally. We could ask the question, what is an expert? An expert is a person who is very knowledgeable about or skillful in a particular area. In our case, this is in the area of understanding the fire engineering design and providing design solutions. As Stephen has captured in his previous slides, the requirements for what types of fire protection systems are installed in a particular building are defined in the fire engineering design. As fire protection engineers, we need to be able to interpret the fire engineering design and extract the relevant information to enable us to provide a pragmatic design solution, which not only offers compliance, but also factors in buildability and cost. Interpretation of and application of standards. There are various standards associated with different types of fire protection systems. These standards define the minimum level of design, installation, commissioning, maintenance, and testing requirements to achieve compliance with these standards. We need to have an ability to interpret and apply the requirements of these standards to our design and documentation. Working with the whole design team, there are many stakeholders involved in preparing design and documentation for a project. This includes architects, other engineers such as electrical engineers, mechanical engineers, civil engineers, could be project managers, and in some situations directly with the client, consultants need to have an ability to coordinate and convey design information with the design team, providing apples for apples tender documentation. The documentation and design that engineers and architects produce ultimately forms a design package for a project, which is issued as a consent package to gain approval from local territorial authorities. This then gets submitted as a tender package to contractors to obtain pricing. As consultants, we need to be able to produce designs and documentation which reflect real-world construction and buildability practices, so as to enable accurate pricing with minimal or ideally no variations to this price during the construction phase. Providing construction advice, we need to be able to monitor the installation process and provide technical and compliance advice to the client to mitigate any potential risks which may affect the construction program, final compliance and certification, or any potential adverse cost implications. How does a consultant differ from a contractor? Broadly speaking, a contractor is responsible for providing all of the material, labor, equipment, and services necessary for construction of a project. An engineer is someone who solves problems you didn't know you had in ways you can't understand. Contractors provide the on-site deliverable product. Consulting engineers aim for practical design solutions to achieve that end, which means a consulting engineer is a person providing professional practical solutions to others. We need to consider the client's scope, the architectural vision, the fire engineering design, the requirements of various standards, the requirements of the certifying inspection bodies, and buildability and cost. What does a client need from us? At Origin Fire, clients ask us for fire engineering, fire protection engineering, passive fire engineering, emergency lighting design, technical advice, full design services for fire protection and passive fire engineering, meeting and attendance, coordination and construction monitoring, to name a few. Our client is really asking us for professional and practical advice, and they're looking to work with a trusted design partner. Clients expect us to interpret the compliance rules, provide the required level of documentation and design to achieve compliance and certification, and apply creative problem-solving skills while understanding their intentions and making cost-conscious decisions, which will avoid costly and time-consuming surprises. What are the types of fire protection systems and what we consider when designing these? There's a significant amount of design, calculations, compliance requirements, and product knowledge required to produce a fire protection design. As we are limited on time, I'll briefly cover some overarching aspects of a few types of systems. There are various types of fire protection systems which may be required for a building. This includes fire detection and alarm systems. When designing such systems, we need to consider the appropriate type of detection suitable for a particular area within the building, with the intention of mitigating false alarms due to the normal operation within that building or area. Fire detection systems can consist of manual alarm systems, smoke detectors, which are typically optical smoke detectors, heat detectors, beam detection, linear and fiber optic heat detectors, and infrared ultraviolet detection systems. As an example, linear fiber optic heat detection systems are commonly used in tunnels, and infrared ultraviolet detection systems, which are basically detectors looking for the radiation emitted from a fire, are commonly used in aircraft hangars. And where required, smoke detectors, heat detectors are located throughout the building. When designing a fire detection and alarm system, we need to consider the limitations of the hardware, the control systems, distribution and coverage of fire alarm zones and panels, networking and interfaces, fire service access requirements, device locations and spacing rules. We need to be able to calculate the correct cable size and insulation rating, determine the maximum length of a particular circuit and the maximum demand of that circuit to ensure there's adequate voltage to all devices. There also needs to be sufficient current in a circuit to ensure correct operating voltages are within defined tolerances. A fire detection and alarm system encompasses an evacuation system. Typically in buildings, the evacuation occurs throughout the building simultaneously. So there needs to be an adequate level of coverage of alerting devices for the occupants. In certain situations, audible alerting devices or speakers are accompanied with visual alerting devices such as strobes. And in some cases, buildings have staged or phased evacuation systems, which where I guess certain levels or floors may evacuate prior to others. Fire sprinkler systems. When designing fire sprinkler systems, we need to consider the storage, the fire load, the rate of fire spread and development, and the extent of potential fire spread in the building or an area. This ultimately determines the classification of occupancy and how much water, typically referred to as the density of discharge or design flow, is required within a particular area to control that fire. We also need to determine the type and size of sprinkler head and the location and coverage of these sprinkler head for particular classification of occupancy. The water supply for a building sprinkler system is taken from the city's underground water reticulation network. Engineers need to be able to perform hydraulic calculations to determine if the water available from the city supply is sufficient to cater for the design flow. A particular building where the city's water supply, I guess, cannot meet that demand, then there's a need for diesel and electric pumps to ensure that there's adequate pressure for the sprinklers to operate. Fire sprinklers can sometimes be required on the external facade of a building to cater for exposure risks from other buildings or other fire hazards such as transformers. We need to perform complex hydraulic calculations to determine the correct pipe sizes and lengths and the reticulation of pipework within a building, just to ensure they're within certain design parameters. There's other types of fire suppression systems which can be utilized to cater for specific risks in a building. These are, as an example, gas suppression systems and water mist systems. Typically in data centers, a sprinkler installation could severely damage servers if they were to operate. A water mist system is better suited as the water mist particles are able to suppress a fire while not damaging sensitive electronic equipment. A fire protection engineer needs to have a strong understanding of the different types of applications of fire detection and suppression systems, as there's quite a few manufacturers of these systems. Engineers must be able to conduct a variety of complex calculations in order to verify a fire protection system's design and seek approval from system certifiers. There are various standards associated with the different types of fire protection systems in New Zealand. These standards cover the design, installation, compliance, maintenance, and ongoing testing for such systems. A few key standards in New Zealand are NZS 4512, which is fire detection and alarm systems in buildings. Second one is NZS 4541, automatic fire sprinklers, and 4510 for fire hydrant systems in buildings. There are other standards and codes of practice which need to be adhered to in order to achieve compliance with these standards I've mentioned, as many of the standards reference other standards. As fire protection consultants, we need to understand the requirements of various standards, New Zealand Building Acts, regulations, and building code, and have an in-depth knowledge and understanding of a range of standards applicable to fire protection systems and how we can apply the requirements of these standards to achieve a pragmatic design solution and achieve compliance ultimately. Fire protection interface with other building services for the purpose of life safety. What does this mean? An integrated fire protection and life safety system combines the various individual systems that make up a building's overall fire safety approach. In other words, an integrated system includes many of the systems located in buildings today. There's a list there of a few types of systems typically found in buildings. It could be gas supply shutoff, fire fan control panels, fire and smoke curtains. Could be even interface with security doors. As engineers, we need to be able to interpret the interfaces required, which is captured by the fire engineering design. And from there, we need to determine the quantity and types and locations of these interfaces to achieve the desired functionality. This requires a high level of design coordination with other building service engineers, such as electrical, mechanical, and access control. Available qualifications in New Zealand related to fire protection. There's multiple education providers offering fire protection qualifications in New Zealand. Engineering consulting firms typically require fire protection engineers to hold bachelor's level qualifications. However, this does not preclude people who can demonstrate a high level of competency, have extensive or strong industry backgrounds, or significant experience within fire protection. However, this is up to each individual firm on their own requirements. Fire protection is a thriving industry in New Zealand. And I guess in terms of a background, if anyone who's interested in the protection of life safety, protection of people and property, and endeavor in a career in fire protection, People typically have backgrounds, and could be from myself. I've completed my bachelor's in electrical engineering, and I found my way into fire protection. Mechanical engineers that typically get into fire protection too, having a hydraulics background. But there's a lot of progression within the industry. A lot of the time, people in contracts such as installers or project managers, designers, find consulting and engineering, I guess, from the initial stages of a project. They want to move up and get involved in the consulting and engineering aspect of the industry. So a lot of the time, there's a progression from contracts into engineering and consulting, and those type of people bring a lot of experience and knowledge with them. But there's nothing stopping anyone from really getting into fire protection. So yeah, thank you for your time. I will now let Vincent take over and begin his passive fire presentation.
Sweet. Thanks, Vinny. Next one is passive fire protection. So passive fire protection is the internal fabric of the building. What stops or slows the spread of fire and smoke between different compartments in a building, and we achieve this by different methods. So if you look at the photograph there, there's a fire in one compartment. Let's say that's another apartment, and you don't want that fire and smoke to spread to another part of the building. So that's achieved using fire resistant separations, and then having fire stops where penetrations are made in the fire separations by various different services. So here, this is just a simple diagram, just showing two compartments. But in an actual building, you have multiple separations, complex connections. So there's various places, or let's say gaps or junctions in a building where fire and smoke could spread, and that's where our passive fire expertise comes in, where we identify these areas or locations and specify products or systems that will prevent or slow down the spread of smoke and fire. Next one. So where do we begin? So as passive fire engineers, we definitely begin with the fire report. So in a fire report, in a typical fire report, you have the fire separation drawings and the fire rating. I've just added a clip here from one of our fire reports. So here, it's there's two apartments, one on each side, and there's a fire protected stairwell. So if you see, almost every fire report will have this drawing showing the fire separation. So here it's showing 30-minute rating here, external wall, and then you have a 60-minute rating between two apartments. So what that means is you need a fire resistance rating of 60, 60, 60 between these two apartments. And here we have a vertical riser that's fire protected. And then you have the stairwell is protected from each of these apartments with a fire resistant rating of 30, 30, 30. So yeah, thanks, Stephen.
I wouldn't be able to see the mouse.
Yep. So that's the stairwell, and you have two apartments. So this is where we start off. So we look at it, and usually the fire report has a a description, and they tell you what the fire rating is, and they have a legend to tell you. So usually, once we get the fire report, we have a look at it. We make sure we understand all the separations, and then we sometimes go back to the fire engineer and say, hey, look, what do you mean by this, or what happens to this wall? Is it supposed to be fire rated or not? So there's a bit of back and forth coordination and collaboration with the fire engineer to understand how the fire separations in a building work. So that's what we do. That's where we get our initial information from. And once that is done, oops. Oh, sorry. Yep. Okay. So what's next? So while we are having a look at the fire report, the architects also get the fire report, and then they decide how to build their fire separations. So in New Zealand, there's various construction materials that you could use. There's concrete, blockwork, plasterboard. Yeah, the list goes on. So the architect is preparing the drawings. They decide what type of walls they want. They choose walls that achieve that fire rating. So if they need a 120-minute wall, they probably go for a blockwork wall. I mean, there are plasterboard systems that would do it, but it depends on their design vision and what they intend to do for the building. So they do that. So we took look at the architectural drawing and see where the fire separations are and what materials or systems the architect is using to build the building. And then we also collect the services drawing from the electrical engineer, the mechanical engineer, and the hydraulics engineer. We want to know what pipes, ducts are going through these walls and ceiling and floor. So that's the second step. So here I have a simple two separate drawings. So on the left, you can see an architectural plan, and just mark the fire separation. So if you see here, you have the fire separation going here, all the way through here, and then this one. If you look at this one, this is a concrete wall. So that's actually a lift shaft there. So that is built out of concrete, and this one is a dry wall. So even though it's two types of construction, the fire rating achieved is the same. So the architects has used two different systems to achieve the same fire rating. So they've decided what to do there. And now here, if you see, there's an opening, but then this is supposed to be a fire separation. So what we usually do is, so that's got to be a fire door. So that's a tested fire rated door that will achieve the same fire rating that's required there. So that's the architecture drawing. And if you look here, you just see a cross section of a wall, a plasterboard wall. So that system achieves FRR of 60, 60, 60. So this is the system from one of the manufacturers. And if you install that wall according to their system, that's the rating that it will achieve. So here they have two layers of fire plasterboard on each side, and the architecture has shown what type of insulation and framing needs to be installed. So that's the second step. So now, just from this example, we know that we have a plasterboard wall and we have a concrete wall. So with that information, we go to the next step, which is the services drawing. So here you can see now, this is from an hydraulics drawing. So you can see that there's a pipe penetrating the 30-minute wall. So we have a lot of services here in New Zealand, especially for water. We use PEX pipe, polybutylene pipe, and then we have copper pipes. And then for the sprinkler system, we have metal pipes, CPVC pipes. For the drainage, we have PVC pipes. What else? Ducts, metal ducts. Yeah, the list goes on. There's various types of services. So what we do is we collect a list of all the services that's going to be installed in one particular building. So if you look at the drawing on the right, you can see that a duct penetrates this fire rated wall, and so we know that we'll need a fire damper that needs to be installed in this wall. Same here at this end. So we look at the architectural drawing and the services drawing and see for these interactions, where these services penetrate the wall, and then we make a list of all the types of different situations that we need to provide a fire stop system. So once that's done, so we've looked at the fire report, we've looked at the architectural drawings, and then we've looked at the services drawings. So now we have an idea about what's going on in that building. So the next one is the fire stop system. That's where we provide our expertise in. So the first one is if the building is sprinklered or non-sprinklered. That plays a huge role in selecting the fire stop system. If it's a sprinklered building, so you don't need an insulation rating. So you only need an integrity rating for the fire stop. And if it's a non-sprinklered building, then you also need the insulation rating. Sometimes different parts of the building are sprinklered. Let's say if I worked on a job where only the basement was sprinklered and the apartments were not. So any fire stop that was installed in the basement did not need a insulation rating, but every fire stop that was installed in the apartments needed an insulation rating. So we make sure we understand, the sprinkler requirements. The next step is choosing the fire stop system. And the fire stop system, according to the building code, must be tested to AS 1530.4, AS 4072.1, and wall construction or ceiling construction must be tested to BS 476, parts 21 and 22. And NZS 4521 is the fire door standard. So we choose fire fire stop systems that are tested to these standards. So what manufacturers do is they take their product, their system, and they go to an accredited fire test laboratory, and then they test it according to this standard, and then they record what was happened, and they give you a fire test report, and that tells you what standard it's been tested to, what rating that fire stop has achieved, and how it was installed. So we get that information from a manufacturer. There are various manufacturers in New Zealand right now, and actually in the last couple of years they've stepped up their game. They've done a lot of fire testing, a lot of new innovative and easy to install products and systems. So I have some example here on the screen. So this one is a concrete slab, and you have a PVC pipe running through the concrete slab. The first thing I want to say is fire stop system is actually a system. It comprises of the substrate, which is a slab in this case, the pipe, PVC pipe, and then the fire collar. So all these three things make up a fire stop system. It's not just the collar. You just cannot swap this for, let's say, an HVAC pair coil, because what happens? Sorry. What happens is the fire resistance rating changes. So in this case, for a 100 mm PVC pipe penetrating 100 mm concrete floor slab, you get a FRR of -120, 120. But if let's say you drop this PVC pipe size to a 40 mm dia PVC pipe, the fire resistance rating changes. It could be -90, 60. So manufacturers use a lot of products, like 40 mm pipe, 80 mm pipe, 100 mm pipe, and they test it, and then they give you the test results. And we choose which fire stop system we need to use based on what we're going to install on site. So let's say on this job, there's a PVC pipe penetrating the floor slab. So we choose, okay, we go to this manufacturer and choose this product. There's various other products that you can install here, like a mineral wool bat and a intumescent wrap, if it is tested to this configuration. Yes. So we have a lot of options. So we look at different manufacturers, look at their data sheets, their installation instructions, how much information they provide, and how easy it is to install. Based on that, we choose the product, and then we put in our spec and we give it to the client. So there's another fire stop system that I've shown here. So this is a brass wing back that's penetrating a fire rated wall. So if you look at this, this is for a water supply, point just below the wash basin. So if you see here, the product is the fire sealant, but this whole thing is a system. So that's a fire rated plasterboard, and then the brass swing back that's penetrating that, and then the fire sealant that's going in the gap. So all this is a complete system, and for a 20 mm brass wing back, the fire resistance rating is -90, 60. So we look at all of this, and then so this makes up one of the systems in a building. So in a typical residential building, we would have about 25 to 30 fire stop systems. Different services, different substrates, different products. All together, they come together and make up a system, and then the contractor takes it and installs it on site according to the system. So this is just a brief example about fire stop systems. Once you get into passive, you'll know there's heaps more, a lot of different combinations. So that's pretty much it about fire stop systems. What does a passive fire engineer do? On a day-to-day basis, I'm not just looking at fire stop systems. That's just one part of my job. I do design the fire stop systems, specify them, write specification for projects. We will help with tender queries, with contractor queries. Sometimes they might have an alternative product that they want to use and they prefer. So we answer any questions or technical questions during the tender stage. We answer questions from the council during the consent process. Sometimes the council might come back to us with RFIs, asking for more information on the testing of the product. So we provide that. A major part of my job role involves construction monitoring. So that's when the building is being actually built. So we visit site at different intervals, make sure all the fire stops are being installed correctly as per the spec. We make sure that the contractor knows what they're doing. They're installing the right product to the right service, as the manufacturer has specified or instructed. Because if you deviate from the manufacturer instruction, then you have to go back to the manufacturer to ask their advice if the system will work or not. So we make sure that the contractor understands this and they stick to the instructions. We also make sure we help with coordinating with different trades. On a typical project, you have people from different trades like the plumbers, the electricians, the pacifier specialists, the fire door installers doing the job. So usually the main contractor doesn't have expertise in each of these items, so they engage us to take care of this, oversee what the contractors are doing and and making sure that they're doing it correctly. So we ensure that they have their proper trained personnel on site, they're doing the quality assurance on correctly. And so so that's a part of our construction monitoring. And usually at the end of the job, we provide a producer statement. That's a PS4 to show that we've what do you say? Monitor the construction, make sure everything's in the right place, and then that it's complying with the building code. So that's construction monitoring is a big part of my role. Like I said, so what type of buildings? I usually work on residential buildings. Pacifier is pretty much needed in all types of buildings: residential, high-rise, terraced houses, commercial buildings, retail buildings, hospitals, a warehouse, even in a zoo. So if you can think of a building, you need pacifier in it. The types of jobs that we do is the first one is obviously new build. We do a lot of new buildings, specifying, construction monitoring, and signing off. We also do remediation and repair. So that's when they find issues with the building. We go in and investigate, see what the current state of the building is, and we provide our advice to the client on how they can fix it, how they can bring their building back to code if it's not. Sometimes we just collaborate with other professionals from the industry on reclad jobs, etc. So it's not just new building. We do it in pretty much every other type of job. What else do we do? Investigation. If you're a building owner and you want to know what the condition of your pacifier is in your building, you can engage us to come and investigate. We'll have a look at all the parts of the building that needs to be fire stopped, and we'll give you a report on the condition of your building. We also act as expert witness and help with litigation. We do a lot of jobs where we assist clients and lawyers. So pacifier, who's it suitable for? It's construction people with construction experience like myself, coming from a building services background, or someone from fire protection background. Also people from a trades background as well. If you've been in pacifier and you want to start moving into design or investigation, this is really good. So so that's pretty much it about pacifier. And if you're interested, you could find out more. These are some of the resources on the brand's website. There's actually a booklet on a guide to pacifier. It's pretty good and detailed. It's been made by some of the big names in New Zealand's fire protection industry. They know what they're talking about, and if you're keen, go have a read. It's free. Download it and read it. It's very helpful. I think that's pretty much it. So we go into the question stage. We have a couple of questions now. Sweet. Okay, I'll read the questions. Many years ago, fireproofing of structural steel and equipment in hazardous environments such as LNG and LPG plants would be achieved by an external application of 50 mm thick concrete, which provided 2 hours protection. Is concrete still used or has been replaced with other products? I can go. Yes,
Yep.
It's been replaced with a lot of different products now. Intumescent paint, vermiculite products. Sometimes clients feel that concrete is not the best solution. It might use up a lot of space. There's plenty of options now. So the next question. What is the next question? Oh, I think this one's for you, Winnie. How important is post-fire stability for residential?
So structural fire.
Yes. How important is post-fire stability for residential buildings like townhouses? What are the actions taken for it? I see there is FRR provided between 2 townhouses. Is that enough, or do we consider post-fire stability? Can you answer that one?
Fortunately, post-fire stability is not a strong suit of mine. So neither is townhouses.
Okay, we could.
That one would have to get back to you on an answer. Sorry.
Yes. Okay. Sounds good. Next one for you, Winnie. For the firefighting water supply, is there a minimum level of service or fire water classification that the council water main provides under SNZ PAS 4509 2008?
Under that standard, there is, depending on whether a building's sprinkled or not, there's a minimum, well, there's defined requirements in there for how much water needs to be available from hydrants for firefighting water supply. Sometimes that requirement for firefighting water supply is cumulative, so it could be in addition to sprinkler water supply. But typically for a sprinkler building falls under FW2 for water supply, so you need to have 750 litres a minute from a hydrant within 135 of the fire service attendance point, and another 750 litres for within 235 of the fire service attendance point. So yes, I guess it depends on the size of your fire cell as well. In unsprinkled buildings, that will determine how much firefighting water supply you need as well.
We'll like to add to that, some councils do specify a minimum. No, Hamilton Council under their, I can't remember what it's called now, that a technical standard for regional infrastructure. That one they specified FW2 firefighting water supply for residential areas and FW3 for everywhere else. Watercare give a stated pressure and flow level as a guarantee, but you'll often find it'll be higher. It very much comes down to get a water flow test as part of your design early on. That would be the main recommendation.
There's some tables actually out there from your councils, which give you some demarcations on the expected FW flows in certain areas. So obviously more industrial areas, that the water reticulation network has been designed to flow FW5 or 6 in some situations. So it's good to try to get a hold of that wherever you're based in New Zealand. And it can be used, I guess, to have an initial glimpse into what a water supply distribution should be in a particular area. But as Stephen mentioned, it's best to just do a flow test to verify what's available.
Sweet. Thanks, Vinny. The next one is, when do you require a structural adequacy rating in FRR?
So with that one, the structural adequacy is about any load-bearing equipment, load-bearing members. So this is columns, beams, your floor slabs, load-bearing walls. You wouldn't have that in a fire-stopping system. You also don't have it in doors or windows. You get a dash XX. The dash YZ, as you've put in the question, those are always for fire stopping or doors or windows.
Okay, thanks, Stephen. Next one for you, Winnie. How do we integrate the smoke spill fans and zone into the fire alarm system?
I guess to control fans in a building, first you'll need an addressable panel, typically. Conventional panels can have relays within the panel, give you clean contacts to operate ancillary services. But I guess you'll have to confirm with the contractor installing the spill fans on the type of contact that they require, whether it's a normally open, normally closed contact. Typically, fire protection requires clean contact relays. So it's just a matter of coordinating where that third-party contractor requires an interface, how many relays do they require, and the type of I guess output that they require, whether it's a normally closed circuit going open or vice versa.
Thanks, Vinny. Stephen, for you, is there a requirement for the peer reviewer to be a chartered engineer, a legal requirement, council policy, or just good practice? If it's a legislation, do you know where it sits?
So yeah, your peer review does need to be chartered. As for where that requirement is, I will have to get back to you on find the information to send it.
Okay, thanks, Stephen. There's one for me. When fire stopping or penetration in a one-way firewall, let's say external wall, do you still need to provide dampers, etc., or are those just for internal fire separation wall? So usually when the system is tested, it's tested on a two-way wall. So let's say there's in a job an external wall. If there's a one-way fire rated wall, the fire stop that we choose will be a two-way. It would be tested on a two-way fire rated wall, and we would use it. It would be kind of more of an overkill, but we can't go lower than the minimum. So we'll provide the fire stop that's two-way tested. So that's what we do. Yeah. Sometimes internal fire separations could also be one-way fire rated, but we use two-way tested systems. Okay, the next one.
I would like to add to that one. If it's an external wall, it depends if you need a spandrel. So a spandrel is a fire rated section of the external wall to stop fire spread between levels of the building. If you need a spandrel and you have a duct penetrating through that, you would likely have a fire damper. If your duct is below the spandrel, your fire engineer might say that you don't actually need to fire rate that based on your distance to the relevant boundary. Ideally, that would be the case, that you don't need to fire rate your external duct penetration.
Sweet. Thanks, Stephen. Next one, Stephen, do you think you can answer that? Do we need to design an IT wall supported by the floor as a cantilever for 0.5 kPa fire load? Is that structural engineering?
So where that requirement is, your tested firewall systems, they will achieve the requirements. So I think it's AS 1530 Part 4 for firewalls. So when they test those, they will put a degree of load on it and also some pressure.
Cool. Thanks, Stephen. How good is the pathway structure towards being a chartered fire engineer? I think this is one for engineering New Zealand. If you go on the website, they have a lot of material about how to become a chartered fire engineer. You'll find webinars and useful links. So I think, yeah, you should visit the Engineering New Zealand website. Cool. The next one, if you are near a water body, say a river, how can that be used as form of supply for fire suppression deluge? Will this require any special approval?
Yeah, for using, I guess, brackish water, you'll need to run that past the fire sprinkler system certifier in New Zealand. Typically in New Zealand, we tend to use tanks as opposed to drawing up from rivers, but if you're in a rural area and there's no other options, that's something you'd have to run past the certifier. There are other standards in New Zealand, for example, for residential homes, where you can use supplies. There's older standards too. For example, in New Zealand, there used to be an insurance standard for fire officers committee that allowed drawing from ponds or lakes and rivers. But any such arrangement you'd need to run it past the certifier.
Thanks, Vinny. How do you detect fire from a nearby building and connect with their system for communication?
With that one, if it's a shared complex or under common ownership, you'll link the fire alarm systems, which goes so it'd be part of the passive fire design, fire protection design, and the fire safety design would also cover that. If it's neighboring property, they would have to have designed their building to protect against fire spread to your property. So you theoretically shouldn't need to worry about it. Obviously, caveat, not everything, don't rely on that.
Yep. Thanks, Stephen. What limiting temperature should we prefer for the intumescent coating of steel members? It's 550 degrees Celsius.
Yes, so that will be specified by the coating supplier and the structural engineer.
Yes.
So as a fire engineers will say, you need to fire separate certain areas of the building. The structural engineer will say, okay, these structural elements need a fire rating in order to maintain that separation. And they'll have a look at the intumescent coating requirement.
Cool. Okay, how about fireproof lightweight thermocol and train concrete panels? I'm not sure what the question is about. Probably, I mean, that's going again in detailed design about how to build a building. And yeah, I think we'll get back to you on that one. What are the major causes of fire and fire spread? Yeah, do you want to answer?
I'm not actually sure. Don't have it. It's largely electrical issues and
Improper storage.
Yeah.
Be one of it.
Negligence.
yeah. We tend not to worry about the specific cause of the fire. We, with the design, you start off assuming that there is already a fire. So, okay, how does this affect the building? A tangent on that, if you do performance-based design, you'll do what's called a challenging fire. So you'll have several fires within your building. You'll assess one at a time. Say, okay, how does this a fire here challenge the life safety of the building? You don't terribly worry about what started it. You just say, okay, there is a fire here.
Sweet. Looks like we're running out of time, so I think we'll have to skip the rest of the questions. Yep. Just go back. This is our contact details, and if you have any more queries or if you want to get in touch, you can get in touch with us, and we are more than happy to assist you guys. That's pretty much it from us. Thanks for joining us. I hope you have a wonderful rest of the day. I'll